Hello, student. Welcome to this topic of scattering phenomena. So now we have to study the this scattering phenomenon using the quantum mechanical aspects. So, as per the quantum mechanical aspects, in a scattering process, a beam of particles is allowed to pass close to a scattering material called a target, and their energies and angular distributions are measured. So this is how we are studying the scattering phenomenon. Okay, so it is a process where a beam of particles will be there. It is coming close to a target material or the scatterer called the target, and their energies and angular distributions are measured after scattering. So during the process, the target may remain in its original state, uh, which is nothing but the elastic scattering, or may move to a different state, which is the inelastic scattering. Because as you know, in case of the elastic scattering, uh, the state of the particle is not going to change. So that is why if the state of the particle is changing means that kind of scattering is generally inelastic scattering. So two possibilities will be there during the scattering process. So the study of scattering is important as it represents one of the best methods of studying the properties of atoms, nuclei, and interaction of elementary particles between themselves and with the atomic and nuclear systems. So, the study of this scattering is so important because of these reasons. It is very highly informative as it is related to the atoms, nuclear systems, and elementary particles, are those things. Even the concept of atom is an outcome of a scattering experiment, which is conducted by this Rutherford while analysis of the alpha scattering. This first time because you have studied the alpha scattering phenomenon where the target material is hit by alpha particles, and first time the Rutherford told that or predicted that there is a central heavy mass which is called as the nucleus, and also the concept of atom is also realized during this Rutherford's experiment. So that is why the concept of atom is realized during one of the scattering phenomena or scattering experiment conducted by the Rutherford. There are two types of approaches when we study the scattering processes. They are one, in this process or in this approach, the differential equation for the scattering of waves by obstacles is set up, and its asymptotic solution is obtained. So here we are setting up the differential equations for the scattering waves by obstacles, and the asymptotic solution is obtained. Asymptotic solution is a nearby solution. It is not the exact solution. Here, a detailed examination of the process in the scattering region is not done. That means we are not going to look at the scattering region, what is exactly happening. So that is the how or way of tackling this scattering process. The second approach is that scattering is considered as a transition from an initial state of given momentum to a final state of different momentum of the same energy. That means we think that the momentum is going to change. The momentum is going to change during the scattering phenomenon. So initially some momentum will be there. And after the scattering, the momentum is going to change, but the energy remains same. The evolution of a rate of transition is done with the help of a time-dependent perturbation theory. So in this way, this scattering process or scattering phenomenon is studied by these two approaches. And now we'll see what is this scattering cross section. Consider a beam of particles of mass m, small m, means every particle will be having this mass small m traveling along the z-axis with the velocity v. It is the common velocity. We can say that it is the common velocity of all the particles. Just for just for approximation. Actually, in reality, the particles may have the different velocity, but here we assume that all the particles are having this velocity v and scattered by a scattering potential v, which is surrounding the target. That means this potential, some potential will be surrounded by, will be surrounding the target material or target atom, and that potential interacts with the incoming particle centered at the origin. The incident particles experience a force only when they are inside a sphere of radius r, which is the range of the scattering potential. That means this incident particles will experience a force only if they are within the region of this scattering potential, which is to be assumed spread spherically over this target material. And there will be some interaction between the incoming particle and the targets and the target particle only if the incoming particle is at least just touching the sphere of potential or inside the sphere of potential. Due to interaction with the scattering potential, the incident particles in general get scattered in all directions. So when they interact with the target particle, they get scattered in all directions. After leaving the sphere of that interaction, where we assume that the potential is spread inside the sphere, they once again travel in a straight lines. They once again travel in a straight lines. The angle between the initial and final straight lines is called as the scattering angle. That means the angle subtended between the two straight lines. One is the initial direction of the one is the line which is along the initial direction of the particle, and the another straight line is in the direction of the scattered particle. The experimental arrangement is shown in the figure. So this is a simple experiment, and here these are a beam of particles which are coming towards this target material, and this small sphere indicates that it is the sphere of potential. That means the target material will be exactly at the center of the sphere, and Around this target particle, we are considering a sphere within which the potential is assumed to be spread over. And when some of these particles are near to or inside the this sphere, they only get scattered. Other particles will go straight away without scattering. So after here, what happens? Here the scattering process takes place, and here here we can place a detector. In this direction, we can place a detector which detects the scattered particles. So this is an example. In this direction, some particles are going, and which are making a cone, so that a solid angle is created here. So this is the direction of scattered particles, and this is the direction of the initial particles. Between these two, this whatever this angle is there, this is called as the scattering angle. So this is the z-axis. We assume that the flux of these particles is low enough so that any interaction of the incident particles with one another or themselves is completely negligible. This is the flux of the particles. Flux means the number of particles per unit area, like that. So this flux of particles, we assume that it is low. The intensity of this flux is low, so that there is no interaction of the incident particles with one another, which is completely negligible. Let capital N be the number of incident particles crossing unit area normal, which is held crossing unit area, which is held, that area is held normal to the beam in unit time. Such a number it is. And small n be the number of particles scattered into angle this d omega in the direction theta comma phi in unit time. So here you can see in this diagram, here this is the small n, and this is the capital N. So here capital N indicates the total number of particles coming per unit area here, but the small n indicates the number of particles scattered in this direction. So this theta comma phi are they are the polar angles or the spherical coordinates, and this phi, this azimuth angle phi, satisfies the orientation of the scattering plane with respect to some reference plane containing the z-axis. So actually this phi is the angle between the scattering plane and the reference plane. So now we are defining this one thing called as the differential scattering cross section. D sigma is denoted by theta comma phi, and is defined as d sigma of theta comma phi is equal to small n over d omega whole divided by n. Where this n by small, where this small n by d omega is the number of particles scattered per unit solid angle, whereas this capital N is the total number of particles which are coming towards the target material per unit area. So it is such a number. Then this is the standard definition of a solid angle in polar coordinates. So this is d omega is equal to r sine theta into d phi, or d theta divided by r square. So actually this r is this r, it is the radius of the sphere, and because this is the cone formed inside the sphere. And here you can cancel this r with r square, and you are left with sine theta into d phi d theta. So this is the differential cross section, means it is the some small area. This is the small area of the total area held, which is in perpendicular to the direction of propagation of the incoming particles. But we want the total cross section, means whatever the whole area which is coming, cross section area coming under this sphere, actually is pi r square. This area is equal to pi r square. So that is called as the total cross section area. So the total cross section sigma is the integral of this d sigma differential cross section over the entire solid angle. So therefore, this total cross section is given by it is integral of a differential cross section multiplied by the solid angle. So substitute the value of this solid angle, and now I am separating these into two quantities, because this quantity sin theta into d theta depends upon the angle, which varies from only 0 to phi, whereas this quantity d phi, it can varies from 0 to 2 phi. So that is why these two are separated. So this is the equation number 2. And both this d sigma, d sigma means differential cross section, and this total cross section have the dimensions of area, and hence the name cross section comes here. So these two are the cross sections or cross sectional areas which are held perpendicular to the direction of propagation of the particles, and that is why these two quantities are having the dimensions of area, and hence this becomes these are defined as the cross sectional areas. For a spherically symmetric particle, this differential cross section is independent of phi, and therefore this sigma becomes, and therefore this sigma becomes, means equation 2 becomes like this, because now this differential cross section is independent of this phi. So that is why this one once because this phi angle is the angle which varies from 0 to 2 phi. Once this becomes independent of this phi, then we assume that this is only the function of this theta, and this theta varies only from 0 to phi. So therefore, this d sigma of theta is written in this integral, and already this integral is there, sin theta into d theta, and this integral of this d phi is calculated. So the integral of 0 to 2 phi of d phi is 2 pi. So that is written here. So therefore, when the differential cross section is independent of this phase angle or azimuthal angle phi, then the total cross section is simply given by this equation. Is sigma is equal to 2 phi into 0 to 2 phi into integral of 0 to phi differential cross section d sigma of theta multiplied by sin theta into d theta. So this is the expression for total cross section, scattering cross section, whereas d sigma of theta is the differential scattering cross section. And generally, these cross sections are usually measured in bonds, and 1 bond is equal to 10 to the power minus 24 centimeter. Sorry, centimeter square. So because these distances are very, very small, because the atoms itself are they are very small, and hence this barn is very, very small area. It is of the order of 10 to the power minus 24 centimeter square. So this is about the scattering cross section. And in the next section, we will see what is this scattering amplitude, and how it is connected to the scattering cross section. Thank you.